Audible?
Yeah. This will be next session. Yes. Okay. Okay. So before we start, so what I was saying, this is winter school, and I'll be talking about very basic work calculation also. I'll be talking what I have done so far. It, things are from various papers and different whatever presentation I see and all. I try to put things together. So before I start, can I ask how many of you are PhD students? Okay, quite a good number. And then how many are from PCBs? Okay.
Some people are on the way.
Okay. Fine. So I'll be telling very basic things. Still, if you feel anywhere that no, I am not able to follow that, stop me there only. Don't wait that I will ask question in the last, because that usually doesn't happen. So you hold me, ask the question, and then we'll move forward. Okay. So as you see, the topic is carbonaceous aerosols, sources, composition, and importance. Importance we all know. Yesterday we have heard many lectures. So all the reason for which aerosols are important, carbonaceous aerosols are also important for that. Those reasons. Okay. So first, very basic thing, what we have in the atmosphere. Now, if you see, okay, see the range, 10 picometer to 10 centimeter. This is 9 orders of magnitude range we are talking about. So what we have between 100 picometer to 1 nanometer, we have gas molecules, we all know. And then from 1 nanometer to 100 micron, aerosols. This question is always asked, that why aerosols means whenever we speak about the definition of aerosol, we say that it ranges from 1 nanometer to 100 micrometer. Anybody can ask that why it is not less than 1 nanometer or more than 100 micrometer. The reason is once you go less than that, you are going at molecule level. So molecules come together, then they take whether liquid, solid, or gas. That is why less than nanometer is not aerosol, and bigger. Why? What is holding bigger side? So once you are reaching out 100 micron, it is very heavy. So it will come down very fast. So it doesn't stay in the atmosphere. So that is the reason you have the aerosol size. Then when we talk about, it is from 1 nanometer to 100 micrometer. And then you have bigger size. You have cloud, fog, rain, snow, rupal, hails. So up to 10 centimeter. You know, means this hails, ole, जो पढ़ते हैं, that can be as big as about 10 centimeter. So this is all we have. Now I have put some different colors here. See, some things are in red, and that also having some size. So say for when I bring mineral dust and sea spray, that is from 1 micron, 1 micron to 1 micron. When I'm putting sulfate, SOA is secondary organic aerosol that we know from yesterday. And soot, it is towards lower sizes, 1 nanometer to 100 nanometer. And then variety of bioaerosols like protein, virus, bacteria, spores, pollen. So all these size ranges are given. So this is all we have in the atmosphere, and they are all linked. For example, lower size particle, they can form from gases, gas to particle conversion. That is secondary organic aerosol formation. So whatever is there is come down by rain or snow or vapor. That is removal. So everything is interconnected in the atmosphere. Now, what is the composition? What is they are made up of? So typical composition, if we talk about, you have organics, you have black carbon, you have secondary inorganics. When I'm saying secondary inorganic means sulfate, nitrate, ammonium, these kind of things. Then you have sea salts. Sea salts are sea spray. So whatever, if you take a sea water, dry it, whatever is there is sea salt. So mainly it is sodium chloride. Then it can have sulfate, calcium, magnesium, potassium also. That is sea salt. And then you have mineral dust. So very obviously, this composition cannot be uniform everywhere. How it will vary? It will vary in time and space with predominant sources. What does that mean? So if you are going to Jaisalmer, for example, so obviously you will expect more of dust. So that dust part will become bigger. You are in very dense forest around that kind of region. You will have too much of organics there. You are sitting in some island. You will have many of sea salts. And then you are in big cities like Delhi or Bombay or Calcutta, then you will have too much of anthropogenic. Depending on precursor, those kind of things will be there. So accordingly, this composition will change. And this is variable in time and space means from place to place. Time means within the day, it will vary. So 24 hours will not remain constant. That will depend upon meteorological condition. That I'm not doing right now. And also with season means meteorological condition will change. Again, it will change. But then what else? It depends upon site. Say same site, we are collecting different size of particles. Composition will be different. You can see that range, whatever range I have put there. Say if you are collecting only 1 micron, 200 micron, you will have more of dust and CSAR kind of things there. If you are collecting only less than 100 nanometer particle, you will have more of soot or SOA or sulfate kind of species. So it will also depend what size you are talking about. Mainly when we say, can I have some what? So whenever just I usually speak less. So whenever I am speaking too much, my mouth gets tight. Okay. And then also, obviously, it will also depend upon the transport and removal mechanism. Transport means what? Say in this room, you are putting some the source I am putting here. So some this agarbatti or dhupatti kind of thing, if you are putting, it will fill the room with those gases. If you have a strong winds, they will take it away. But if it is close, calm winds, it will accumulate. So it will depend. Transport means winds are taking that far away or things are holding. So that will also decide concentration at any place. For example, when we talk about Delhi, same sources in different season, you will get different concentrations. So if you are very smart, you will go when it is on peak and you will put something, and then you will say that see, it will decrease. And it will decrease because of meteorological condition, and you will take the grade. Oh, see, means I did something, so it is going down. So we have to understand. Okay, let us move further. Now I'll be talking mainly on. So till last slide it was general. Now we'll talk about carbonaceous aerosol. When we say carbonaceous, it means carbon containing aerosol. So what are the carbon containing? One is inorganic carbon, which we usually don't consider. So carbonates are also carbon containing aerosol, but we don't consider them. We know they come from soil, so they are usually ignored. Then you have black carbon or elemental carbon, and then you have organic carbon. Below that, I have also put primary or secondary. Primary means particle coming as a particle in the atmosphere. Secondary means it is forming in the atmosphere. So some gases are there, they are forming. So that is secondary. And if it is coming as a particle, it is primary. Black carbon is always primary. Organic carbon can be primary or secondary, depending upon their sources. Why they are important? Just let me tell briefly. Black carbon, we all know, it absorbs all radiation after CO2. This is the second largest species in the atmosphere, which is causing warming. It can affect glacier. People talk about that deposition of black carbon on glacier lead to melting. Then it has variety of health effects. Organic carbon, it used to be considered as a scattering type of species. That means it scatter incoming solar radiation and add to cooling. It is effective cesium because mostly it is hygroscopic. It also have many health effects. But in recent decade, it was shown that all organic carbon is not scattering. There is a fraction called brown carbon, which is absorbing fraction of organic carbon. That is called brown carbon or BRC. That can also be primary or secondary. Now we all know what is the meaning of primary and secondary. Okay. Unlike black carbon, so black carbon is also absorbing, brown carbon is also absorbing. But unlike black carbon, which is absorbed throughout the wavelength, brown carbon absorbed in near UV and visible region. So, but means whenever we are talking about black carbon, anytime is the most absorbing aerosol species in the atmosphere. But abundance of brown carbon is very high compared to black carbon. It can be 2 to organic carbon. We all know means the ratio of OC to EC. It goes up to 10, 20 also. So and that fraction is BRC. So abundance of BRC can be very high than BC. And that is why it is important to consider brown carbon also. People have shown that whatever relative forcing because of BC, about 1/3 is because of all absorbing species, 1/3 is because of brown carbon aerosol. Okay. Now let us just see this. So overall, what I am saying, you have non-absorbing organic carbon, which is scattering type organic carbon. You have absorbing organic carbon, which is brown carbon, and then you have absorbing black carbon. Black carbon usually is, we will not talk further about this. So first we have graphene-like structure. Things are coming together, and then you are making this concentric square kind of thing. They are coming together and forming lacy aggregates. They can remain open or they can become compact and aggregate. So overall, this is black carbon, which is highly absorbing. Somebody sometime can ask you that why black carbon is black. Means what is so specific that it is black? We all know that any color what we see depends upon what radiation is reflecting back. If everything is reflecting back, it is white. If everything is absorbed, it is black. Because of this structure, it has the ability to absorb all the radiation coming in, and that is why it is black. Okay, so this is the structure about black carbon. What about organic carbon or brown carbon? So let us see that. So now we will be going little complexity involved in organic aerosol. Sulfuric acid, wherever you go, it will always look like this. You will have sulfur, 4 oxygen, 2 hydrogen. Sulfuric acid will always be like this. Black carbon, we have seen, it can be structured like this. This is lacy structure, or it can be compact. It will be like that. But when you are talking about organic carbon, in our 10th, 12th, we studied alkane, alkene, alkyne, aliphatic compound. Then there are aromatic compounds. Then there are various derivatives of alkane, alkene, aliphatic compounds, various derivatives of pHs. So there are too many species in the atmosphere. So when we say organic carbon is one word, but that is composed of wide variety of chemical species, and they have different properties. So that makes this very complex, most complex part of aerosol in the atmosphere. So as I wrote, composition is largely unknown and variable for organic carbon. Moving further, what about brown carbon? So brown carbon are usually high molecular weight organic species with very big structures. Any absorbing species must have a large network of conjugated double bonds. What it means, I will tell in a minute. Large fused ring structure or aromatic monomers connected to a large conjugated system. This is conjugated system is alternate single bond, double bond, single bond, double bond, like that. So these are some of the monomers which come together and form brown carbon. So this is typical brown carbon. So fused aromatic ring, especially with NO2 and COH type of functional group. So then somebody will say that, so okay, black carbon because of structure it was absorbing. Why brown carbon absorbed? So if somebody had studied molecular orbital theory, or even if you have not studied, doesn't matter. In molecular orbital theory, electron can jump from bonding and non-bonding orbitals to empty and de-bonding orbital. So if you are getting sufficient energy which can jump from one level to another level, that kind of species will be absorbing. And whatever the energy difference is there, that wavelength will absorb. Usually that wavelength is near UV and visible region, that is why brown carbon absorbs in that region. Okay. Now, if we are talking about black carbon, this is very famous paper, Bond et al. 2013, and whomsoever is studying black carbon, probably he or she would have seen this. Just quickly go through this figure. So what are the sources? Residential cooking, agriculture burning, open burning, like savanna or forest fire, brick kilns, oak making, petrochemical, flaring, industrial emission, off-road vehicles, etc., etc. These are the sources of black carbon in the atmosphere. Black carbon, I told it is primary particle. Then there is, along with whenever you are combusting these many things, which is giving you black carbon, it will also give other species. They all come together and they go to the atmosphere. in the atmosphere. What it does, so black carbon, we all know, it absorbs the incoming solar radiation and causes warming. It has many other effects also. So people have shown that now within the atmosphere you are increasing the temperature. We all know that if temperature is high, the holding capacity, water vapor holding capacity will increase. So it will affect the precipitation. So once we are going up, we know that temperature decreases. But if you are increasing the temperature, that means you are not allowing water vapor to make this cloud and precipitate. So this is the another effect of black carbon. Then there are many health effects, and then glacier I was talking about. If it is falling on glacier, it can cause melting. So these are the sources and effects of black carbon. Let's move further. What are the major sources of organic aerosol? Right now I'm talking about natural sources only. So natural sources means you have pollen, bacteria, virus, fungus, algae, plant debris, all these things which are there in our surrounding. With winds, it can come in the atmosphere. They are the primary organic aerosols. So people have studied that the natural primary sources may be as large as dust or sea salt. That means about thousands of teragram per year. And if we talk about fungal spores alone, that is about 50 gram per year. That is the contribution of organic carbon, natural organic carbon, to the total aerosol in the atmosphere. But if you remember a few things, you remember initial slide, I said with size it will vary, composition will vary. So most of these things will go in bigger size. So which size particle you are collecting, that will also decide that what composition you are going to get. Okay. Other sources. So that I was telling the natural sources. Now you know that we have fossil fuel burning, you have biomass burning, and there can be direct emission. Direct emission is primary particles. Then you have biogenic sources. This terpene and isoprene, these are VOCs. VOC means volatile organic carbon. This is gas. So different trees and plants, they emit VOC. This VOC in the atmosphere oxidizes and come together, further oxidizes, come together and form particles. That is called secondary organic aerosol, SOA. So out of total secondary organic aerosol, if you see about 80% is because of natural, or we call it BVOC, biogenic VOC. And then others are from AVOC. A means anthropogenic. Anthropogenic VOC, which is coming from this various kind of fossil fuel burning or industrial emission and all. Once things are there in the atmosphere, they form, and that is called secondary organic aerosol. So now we understand black carbon source, organic carbon source, organic may primary and secondary source. If we talk about SOA, I was in last slide I was showing about thousands of teragram per year for organic carbon. If we are talking about secondary organic aerosol, it is estimated to be somewhere between 25 to 200 teragram per year. Okay, nobody is stopping me. That means I am very clear. Thank you. So, any questions so far? Please ask in between.
Yes, please interact. And I think, sir, there are some people from other departments also, some MSc students also.
Anyone means right now, whosoever is sitting here, any place, if you feel any question or something is coming in your mind.
And take best benefit of this session.
Yeah, that is the reason. So I am coming all the way. So whatever I know, at least I can share. Let me make a disclaimer. I don't know everything. It may happen that you ask and then say, I don't know. But we can interact.
Sir, in Ladakh, I come from Ladakh. At Khatung La Pass, there are lots of vehicles, and there's snow and glacier as well. So people are mostly worried about this black carbon. There are only vehicles and no other source of
fossil fuel you are saying. Yeah.
So is it a thing to worry about that black carbon at Khardungla right now?
Black carbon is a matter of worry for many reasons. For glaciers, for climate forcing, for health, all the things. Black carbon is porous, so it carries many porous.
Yes.
In between there is a space, and many times there is many toxic metals sit inside, and it is very fine inside.
Yes.
Fine particles has very deep reach in our body, so they can reach. So in all the other aerosols are sometimes positive also. Positive means they are good for us, but black carbon is always black, negative. Then, so we were talking about all these sources. Now, not only sources, some other thing, dynamical change in organic aerosol composition in the atmosphere. Now, what is that? Say some sources has emitted, and you have organic compound. This whatever line you see, each band is carbon. So each band is carbon. So some organic compound is there in the atmosphere, and then it is in the air. Then what can happen? Oligomerization. What is oligomerization? It is small scale polymerization. So that means many oxygen molecules will come together and they form bigger molecule. So this is possible. What is the other thing? Functionalization. That means it will interact with the ambient oxidants and something can oxidize. So for example, whatever was there, now alcohol group has attached. So the moment this thing happening, it will decrease the volatility of the aerosol, and O by C, oxygen to carbon ratio, will increase. What is the meaning it has? That we will be talking a little later. Then there can be fragmentation also. That was long chain compound and something, because of something, it breaks in between. So that will increase the volatility of the aerosol. Composition may change, and that will depends upon where the bond breaks and what caps end. So this is all. Means there we have multiple sources. Now we have many things, dynamical changes in the aerosol organic composition. So that is why organic aerosol composition is, as we saw, it is dynamic. It is not easy to study and also very big headache for bottling, because there are so many processes, you don't know all the processes. People are trying to understand those things. Okay, so now the question is, how do we understand the major sources? Now I told all the complexity, sources, process, dynamical changes and all. So how do we understand the major sources and processes affecting the abundances and characteristics of ambient carbonaceous aerosol? So what we do? Okay. So to study the broader characterization, we study EC, elemental carbon, OC, organic carbon, VRC, brown carbon, WSOC is water soluble organic carbon, and WS1 is water soluble organic nitrogen. This will give us broader characterization of organic aerosol and some idea about the sources. How it gives this, now if we have all these species, how do you know that what we learn, what we are learning from those data? So for example, OC and OM by OC ratio. Try to understand the difference. So I think you will be seeing that instrument from Sunset is going to tell you that you are measuring organic carbon, not organic matter. There is a difference. Carbon means, say, I have given example, glucose. So glucose is C6H12O6, but carbon is C6 only. Right? So what you will measure is C6, but what is actually there in the atmosphere is whole glucose. So if you take the OM to OC ratio, OM is, if you add all of them and divide by C6, that will come to 2.5. So OM to OC ratio is 2.5. But suppose you have some other compound like benzopyrene, and if you see the mass balance, so you will see that OM to OC ratio is just 1.06, depending on the number of carbon versus hydrogen. But when we are talking about the aerosol in the atmosphere, neither you have only sucrose or glucose or nor only benzopyrene. There is a mixture of variety of compounds. So that means ratio will be somewhere in between. So typically, and organic aerosol, when we are talking about, people have reported is somewhere between 20 to 80% of the total organic aerosol. Now, what would be the 1 by OC ratio? Typically, what people consider? Oh, it is then there only. 1 by 1. So, average 1 by OC ratio, people take 1.6 to 2.2. 1.6 is when there are fresh aerosol. Fresh means what? Whenever things are coming in the atmosphere, mostly they are hydrocarbons, and then they start getting oxidizing. Once they oxidize, you are adding more organic oxygen, nitrogen, sulfur. So when you are adding those things, then OM by OC ratio is increasing. So fresh means whenever it is fresh, you will have lower ratio OM by OC. More it aged or oxidized, higher the ratio. So if you are sitting at some place, say you go and sit at the top of some mountain, there is no source in the vicinity. Everything is coming from the far. Then you will take around 2.2 ratio. But you are sitting in Delhi, where many sources are in the surroundings only. Then you will take the ratio 1.6. somewhere between 1.6 to 2.2. That is what people have reported. Now, what you will learn, say, now he will also tell you OC to EC ratio, and you will get some ratio. It can be low, it can mean what is very difficult. Somewhere you will get around 1.5 to lowest, and higher side you can go as high. There is no limit actually. There can be all organic carbon, no black carbon. To higher side, but typically you get up to 10, 20, like that. So what we learn from that? Simple from OC by EC ratio. So if this ratio is high, that means things are coming more from biomass burning. If this ratio is very low, that means they are coming from fossil fuel. So that is typical. That is what I said, broader characterization using this. And then what else? Over India, I have listed many studies. People have reported OC by EC ratio from 2 to 25 at different places. Okay. Then WSOC. WSOC is water soluble organic carbon, which is a measure of aqueous SOA. Aqueous means which is water soluble. Secondary organic aerosol, we saw what is that. So if it is water soluble, you will caught. So mostly secondary organic aerosol is water soluble. So usually WSOC is considered as a, people take it as SOA. Now if you are taking the WSOC by OC ratio, OC is total organic carbon and WSOC is water soluble fraction of it. So maximum it can how much? It can go 1. That means all organic carbon is water soluble. Minimum how much it can be? It can be 0. There is no water soluble organic carbon. So that means ratio will be somewhere between 0 to 1. But whatever ratio you are getting, you can say that this much secondary aerosol you have in your sample. So this is typically used that way. What ratio is reported? 0.2 to 0.95 over different parts of India. And then WSO and WSOC ratio. Whenever people are talking about the nitrogen budget, mostly they talk about ammonia and nitrates. Organic nitrogen, they usually don't consider. Which is, if what people have reported, if you are talking about urban region, it is about 10%. But if you go to marine region, people have reported about 30% of total nitrogen is organic nitrogen. And nitrogen budget, if somebody is doing this related things related to ocean surface water biochemistry, that is very important part. So you have to consider organic nitrogen also. So you can use WSO and WSOC ratio to get how much of the total of water soluble organic carbon, how much is nitrogenous. So that will give you, and that can be get by WSO by WSOC ratio. So as I wrote, for urban region it is about 0.1, and if you go to marine region it is about 0.3. Nobody is stopping. I'm so clear. I'm taking things positively.
You should
I'm
stop.
presuming I'm very
Sir
clear.
also gets time, no? Sir gets break at least. Otherwise he has to talk.
Otherwise I have to drink water in between. Okay, let us move further. Now, so till previous slide, I was talking about the bulk thing. That means total OC, total elemental carbon, WSOC. Now, what if you do the speciation? This was started, in my knowledge, by Shaw and Kass, and they have done this speciation of organic compound. So you see, ambient concentration, and only 10% of organic they could quantify, and they were alkane, fatty acid, different phenols, lipoglucosan, other sugar derivatives, and only about 10% of the total organic present. So that means whatever complexity we were talking about in the beginning. So here you can see now. So you are doing too much of work, still you are able to quantify only a few species. You are not able to quantify what are other things. So you also don't know that what effects they are causing, right? Because you are not even able to identify them. So what do we learn from organic speciation? Say, I already got WSOC, OC, EC, and from that I told you, from ratio I can tell source, from our secondary, primary, those things I am telling. So what is the extra benefit I am going to get if I am doing organic speciation? So let us try to understand that. Okay, so people measure polycyclic aromatic hydrocarbon or PHs. PHs for health, they are very well known carcinogens. Yes, they can cause cancer. Simple pH. Now, when they are in the atmosphere, they are derivatives. They can be oxy, chloro, or nitro derivatives, and they are much more toxic than compared to their parents. So that means if you have pHs, and that also is aging they can be very harmful for your health. pHs contribute less than 1%. Mass wise, if we say less than 1% to the total organic carbon, but they carry very important information. Like the study, Puneet Verma and Prashant Rajput, their PhD was on pHs, and what they have shown that they took the different ratio on y-axis and x-axis. There are different ratios. So different. I have listed these pHs, so different ratio, and using those ratios, you can say that whether whatever aerosol you are collecting, they were from paddy residue burning, or from wheat residue burning, or from forest fire, or from coal combustion, using those pHs and their ratio. Okay. Moving further, sugars. People measure sugars. I mean, when we are talking about sugar, not what we are adding in our tea. Sugars, when we are, some of the things are listed here: levoglucosan, galactosan, menosan, erythritol, mannitol. All these things are listed on the y-axis. Among these, most important is levoglucosan. Why? Because it is a very good proxy of biomass burning. So any biomass, when you are burning, it will emit levoglucosan. It is produced during the pyrolysis of cellulose contained in biomass, along with the other derivatives like mannose, galactose, and breakdown of cellulose, aliphatic and oxygenated compounds. So as I wrote, levoglucosan, manosan, and galactosan, they are unique markers of biomass burning derived. BB means biomass burning derived aerosols. Erythritol, mannitol, they are a tracer of airborne fungal spores. So using, if you have this compound in your aerosol, now you can say that okay, this fungal spores are also contributing to the aerosol we have collected. If we are getting erythritol and mannitol, and sucrose is a marker of airborne pollen grains. So now, see, if you are measuring only organic carbon, you are saying fossil biomass. Once you are doing speciation, now you are able to tell more and more things about the sources of different organic compounds. Going further, people also do dicarboxylic acid, or they also call it diacid. This is all part of water soluble organic carbon. This is the figure I have taken from Deshmukh et al. And what it tells, diacids are the fraction of glucose, and dice is a unique fingerprint to identify atmospheric processes, that is photochemical formation or degradation. Say if you have, you are seeing this side. So if you have this kind of compound, that will tell you there is photochemical formation. And if you have more of this kind of compounds, that means those compounds are degrading. So by measuring this acids, you can say that. So if you recall, dynamic changes we were talking about, this is a result of dynamic changes. Different compounds, something is getting increased, something is getting decreased. So if you are measuring carbonic, this diacids, we can study those things. What else? Elemental issue. So one OCEC we already talked about. Now AMS, I think people are here from AMS also. Yes. So it gives you in second half, I will be giving another lecture and other techniques. Then we'll be talking in detail how it measures. But right now you take it from me that you got organic compound and you got how much is H by C, how much is O by C. And those dotted lines are oxidation state of those aerosols. So if say whatever data we got, if we throw on this plot, so they can fall on some lines or in between the lines. Okay. So from what are the information we can get out of it? Say what slope you get in any xy plot, what is the slope? Y by x or delta y by delta x, right? So slope will be h by c upon O by c, or we can say h by O. So if you are adding h or keeping the O constant, it will be positive. If you are removing h, adding O, it will be negative. So what happens? In first case, what do you see? H remains same. If you are, say, you are removing H and putting OH. So H is in a way same, but you are adding O. The slope is 0. Delta is 1, 0 by 1. So slope is 0. In second case, dicarboxylic acid, you are adding 2H and adding 2 O's. So delta will be -1, 2 by 2, -1. In third case, if you have ketone aldehyde kind of compound, you are losing 2H and adding 1 O only. So slope is -2. Now, when you are throwing the data on this, say if it is falling all on third line, you will say that these kind of compounds are there. If it is falling in between, you will say mostly carboxylic acid kind of compounds are there. If it is falling on alcohol, there alcohol type of compounds are there. And if they are falling in between, then that means there is a mixture of that. And then you have oxidation state also. That I will be telling in some other figure. Okay, let's go further. Okay, I'm trying now.
Sir, what does it signify? Previous one.
You can take mine.
What does it signify?
Take,
I will,
please take
I
mine
put
and
here, so
ask
I will
for
repeat the
answer.
question and then I will answer. So by 2 AMS, you are measuring all these aerosol and you have put whatever data you have collected, you have thrown on this figure. And then you are seeing that where it is falling now, those data points. So with that, you are telling, because what you are measuring is all HCO, different MYZ also, that I will be telling in the next class. From that, depending upon where compounds are falling, you can say that this organic aerosol what we are measuring are mainly composed of whether alcohol or carboxylic acid or aldehyde type of compounds or the mixture of them. Okay. Then oxidation state of organic aerosol. This I have taken from this very nice paper, Kroll et al. Y-axis what we see is average oxidation state. Carbon oxidation state from where to where it can vary? From -4 to +4. Methane -4, CO2 +4. So somewhere it will be in between. X is number of carbon atoms, and more towards right are less number, more towards left is more. And on the top I have shown this figure. Now, if you remember, when I was talking about dynamical changes, I was telling that different type of processes are there. There can be oligomerization. Oligomerization means same compound coming together. So oxidation state will remain same, and number of carbon will increase. So it will go in this direction. If you are looking there, it will come this way. If there is a functionalization, number of carbon is same, but you are writing different functional group. Oxidation state will change, increase. It will go up. If there is a fragmentation, number of carbon will decrease because of fragmentation. And depending upon what cap ending, it will increase slightly increase the oxidation state. It will go like that. So that means if you are putting all the data on this plot, you will have idea that how organic compounds are behaving. This is mostly important if you are doing some controlled studies. This is something you are burning, and then you are seeing the change in composition. That will tell very clear with this. Okay. Then this is, I think, so least study in India. Our group has started this kind of a study. This isotopes, dual isotopes. We know carbon has 12, 13, 14, 3 isotopes. Most stable is carbon. And usually whenever we are saying carbon, we are talking about 12C. But suppose if you have something and you can measure 13C and 14C. So what we learn from that? Say I was talking about fossil or biomass. So when we say 14C, 14C is radiocarbon. And how much radiocarbon you expect if it is say you go outside, any leaf you take out, how much 14C you expect? Whatever is there in that atmosphere, ambient CO2, because it is making food from there. So that is as of today, C14. C14 is a natural radioisotope which is continuously forming in the atmosphere. This probably carbon dating. Have you heard? Carbon dating you must have heard. Present day carbon 14 is whatever is in the ambient atmosphere, means CO2. So that will be there. Say so carbon is coming from fossil. Fossil means what? Which is lakhs of years old, right? So coal or oil buried in there is no 14C because half-life of 14C is 5730 years, or roughly 6,000 years. So within 10 half-life, it is all gone. So within 50, 60,000, everything is gone. So if it is older than that, there will be no 14 carbon. Now I got the aerosol, and I am measuring FC is the fraction of 14C in aerosol. So if it is coming 1, that means everything is contemporary of today. That means it has to come from whether leaves or it can be VOC and whatever, but it is from contemporary carbon. It is 0. That means whatever carbon you have collected, there is no 14C. That means it has to come from fossil fuel. And if it is in between, you can say relatively. 30% is from here, 20% is from there. Okay. So 14C uniqueness is, this is very difficult. You need very big instruments. I am fortunate that in my lab we have acceleration mass spectrometer, so we could measure that. In India, I think two right now, 2 AMS are there. In aerosols, people are not studying so far. I don't know if you get idea and tomorrow you want to work, but it will give you very. Levofloxacin is also used as a tracer of burning, but levofloxacin is unstable chemically. This is very robust proxy of fossil versus bio. If you want to calculate, this is the most robust proxy, 14C or FC. Then what is the role of 13C? Means why I'm saying dual HO. When I'm saying fossil, it can be coal or it can be oil. How do you know it is coming from coal or oil? Right? When I'm saying biomass burning, it can be some grasses burning, it can be some trees burning. How do you know it is coming from tree or grass? There 13C is coming to picture. Because 13C signature are different for, say for example in this figure, the liquid fuel coal combustion. So solid liquid 13C will be different. Same way C3, C4 type of gases, there are different type of thing. 13C is different. So now again, whatever aerosol we have, I have thrown on this. This I have taken from, I have not taken my own paper, but I have taken this one, Major et al. And if you throw the data on this, you say that okay, this much is from fossil, this much is bio, and within fossil or within bio, this much is from C3, C4 type, or this much is from liquid or solid fossil. Okay. So with this, now I'm coming towards the end. So now I'm going to summarize.
So can I interrupt?
Yes, please.
So what kind of sampling protocol we need to
See,
use
it can be-
for performing such kind
Because
of?
it is for others also. You can repeat the question so that others can also.
So if I understand properly, then obviously sampling will play a very, very crucial role here. So what should be the sampling protocol?
Okay. So when we say sampling protocol, actually that will be my next lecture. But since you asked, not only this, any aerosol you are collecting, sampling protocols are important. Say whatever is there in that atmosphere, you are collecting, say right now we are talking about filter, you are collecting on filter, and that is what 24 hours. Okay. Now you know something about primary, secondary aerosol. Secondary, when we talk about, they are mainly usually volatile. That means during daytime, part of it can evaporate and go back in the atmosphere. Nitrate, ammonium nitrate is again volatile. Again, it can go back. So that will be there. So whatever you are collecting. After collection, then you know the way we do 19 minus defriger you keep, then like. But that bias, if you are doing filter sampling, will remain. Because you are analyzing whatever you have collected. If something is gone, it's gone. That is the benefit of online. But 13C, 14C online is not yet available. But if you are doing online, then this artifact will go.
Sir, emission of black carbon or brown carbon is dependent on temperature or not. Their emission, if temperature is high, it is black carbon or brown carbon.
No, it is not that way. So whenever you are combusting something, if it is perfect combustion, so you will make black carbon and ash. If it is incomplete combustion, more incomplete, more organic carbon you will have in that. Brown carbon is organic compound. Black carbon is elemental. So composition wise they are different. Both have absorbing nature. One has because of its structure, other has because of type of compound it has. But I was saying means electron can jump from bonding orbital to anti-bonding orbital. Yeah. Okay. So let me summarize now. So carbonaceous aerosols are considerable and most complex fraction of ambient aerosol coming from a variety of natural and anthropogenic as well as primary secondary sources. Bulk composition of carbonaceous species, which are listed here, helps in studying their broader characteristics. Speciation of organic compounds, which are listed, and their topic composition offers greater insights in their major sources and process affecting their characteristics. Measurement with online instruments like a chart of EMS, pulse, LWCC, accelerometer, and all provide better understanding of the sources, characteristics, and meteorological dependence of carbon schedule. So this is third point is what you were asking. And there is lot to be understood about carbon schedule actually in the whole world and mainly in India because we are much limited studies for India. So with this, I wish to thank you all. And if there are questions. Okay, fine.
Thank you so very much, sir. I think we'll be taking questions over tea, and sir is taking another lecture after lunch also. Now I would request Professor Deepak Pithania, sir, chair of this session, to thank Professor Neeraj Rastogi, sir. It was really an excellent one, and I want to tell we are live on YouTube, and the link will be shared. Listen to the lecture again and ask more questions post lunch because sir is here today with us. Now I would invite Professor Deepak Pithania, sir, for his quick closing remarks, and then we will start another session after tea because tea is ready outside. Thank you.
Thank you, Dr. Stogi, for a nice talk, explaining very beautifully the difference between various carbons, black carbon, brown carbon, or carbon black, organic carbons. तो मैं छोटा सा कोट करना चाहूँगा, स्टोरी छोटी स्टोरी। एक बार टीचर था, उसने सरप्राइजली जैसे आपका एग्जाम भी चला हुआ, क्लास चल रही है, सरप्राइजली एक क्वेश्चन की मैं आपका एग्जाम ले रहा हूँ, एग्जाम ले लेता हूँ। मैंने क्वेश्चन पेपर दिया, क्वेश्चन पेपर में कुछ क्वेश्चन थे, कुछ दे दिया उनको, तो टीचर ने कहा कि उसका बैक साइड टर्न करो, उसका जो क्वेश्चन पेपर था, तो उसके बारे में लिखो क्या था। तो बच्चों ने देखा कि बैक साइड में कुछ नहीं है, खाली एक स्पॉट था, छोटा सा स्पॉट। वो तो लिखें क्या। उन्होंने टीचर ने कहा जो मर्जी लिखो आप, जो भी आपको नजर आ रहा है उसके बारे में लिखो। तो कईयों ने कहा ब्लैक स्पॉट, उसके बारे में लिख दिया थोड़ा बहुत। तो जब टीचर ने उसका आंसर देखा तो इस सरप्राइज, उन्होंने कहा कि आपको ब्लैक तो नजर आ रहा है, लेकिन व्हाइट जो इतना बड़ा पोर्शन पूरा पेपर खाली है वो नजर नहीं आ रहा है। That means we have to also along with the soul, because soul, the composition of soul, it get affected by a large number of the factors. We have to look upon the factors, how they get influenced and how we can contribute to control the release of the aerosol. So thank you very much for your presence hearing, and let's meet in the team.
Thank you so much, sir. Sir is our Dean Research Studies also. I once again thank you, sir, for chairing the session. I request Dr. Richa Kothari, ma'am, to present a memento, and thanks, sir, for chairing the session. Because everybody is so busy and out of the busy schedule, if you are coming and chairing the session, it's a pleasure. Thank you one and all. Now we'll move for tea, and after 15 minutes quick break, we'll start next session. Thank you.